Hello, my name is Spencer Jason, and I led the Capstone project developing a prototype device for advanced wound care treatment. Second and third degree burns are difficult to treat and can potentially be fatal. Immediate care is important for severe burns because of the infection risk and tissue damage to the body. Skin grafting is used for these injuries, but there are some major drawbacks. It is not available in the field setting, so combat medics aren't able to prevent infection on a burned soldier. Skin grafting is also expensive and time-consuming for the clinic. It is notoriously painful and can leave scarring and discoloration on the victim. Severe burns make up 8% of combat injuries in the military, and this is a problem they are looking to solve. As for the civilian market, 40,000 citizens in the US are hospitalized annually for second and third degree burns. The global burn care market was valued at $2.3 billion in 2021 and is projected to increase at 7.1%. There is a major potential to improve the healing process and outcome and reduce resources spent on burn victims.
It is a portable handheld wound dressing device designed to deal with severe burn wounds and for emergency treatments. With a press on the trigger, the device sprays nanofibers on the targeted wound and forms a thin layer of nanofiber to cover the wound. The spin heel is powered by rechargeable batteries, allowing for use on the field and at the operating table. The spin heel uses disposable cartridges, so operators can easily remove empty cartridges and replace with a new one. The spin heel also uses the patent technology of force spinning to produce nanofiber. The force spinning allows us to generate nanofibers using only simple mechanisms.
We would like to propose the alternative solution for wound treatment, nanofiber dressings. Nanofiber dressings have been proven to regenerate tissues,
with their structure mimicking human skin layers, allowing cells to move into their porous structure and start the process of cell growth, leading to tissue regeneration.
Additionally, incorporation of antibiotics or antimicrobial substances into nanofiber dressings can help to prevent or treat infection risk at wounded sites.
To best deliver our value proposition, we're aiming for a small, lightweight, durable, and balanced product. Other qualities like quick application time, a disposable cartridge, and accuracy are also focused on. To explain how the device works, first we have to know what is force spinning. So force spinning is a method of producing nanofibers using centrifugal force to draw polymer solutions through a spinning spinner to form fibers in nanoscale. If the centrifugal force goes larger than the surface tension between liquid molecules, it can break the link between the molecules and force them to move. That will stretch out the liquid and form fiber jets. If the fiber diameter is in nanoscale, then it is called nanofiber.
So why use force spinning instead of electrical spinning? Well, electrical spinning is a mature technology and has been used for several years. But as you can see, the electrical spinning machine is huge, and it is impossible to carry this thing around. Also, building this machine costs a lot, and its throughput is relatively lower, so that means it requires a longer deposition time to generate the amount of fiber that we need. In other words, lower efficiency. So, compared with electrical spinning, the biggest advantage of the force spinning is the mobility. Here is the force spinning device. This device is driven by batteries and motors, so users don't need to carry any power cords or power supplies. Finally, force spinning is a safer method compared with electrical spinning to generate fibers. Since electrical spinning requires a high voltage to generate fibers, but actually provide the risk for users to get electrical shock.
To provide a better understanding of how the device works, here's an animation showing the key components in our device. First, a 3-phase brushless DC motor is connected to a microcontroller and a trigger. Once the trigger is pulled, then the motor spins. For the power transmission, we're using a 3-to-1 ratio bevel gear pair to increase the rotation speed. The airfoil spinneret contains the polymer solution with small 0.5mm orifices. When the spinneret spins, fibers can be ejected radically from the spinneret. Finally, the device uses a fan and an airfoil spinneret to create streamlined airflow. When the device is spinning, the fan creates a steady airflow towards the front. The nanofibers enter the flow and move towards the nozzle from the device, and fibers can be deposited onto the target.
Next, I'm going to demonstrate our device. As you can see, to spray the fiber, simply turn on the switch, pull the trigger, and fibers come out. After applying the nanofiber mat on the wound, doctors can still observe the wound by spraying the water on and make it transparent.
We have developed the prototype for a portable nanofiber applicator for applying wound dressings to people. It is targeted towards military applications, addressing accessibility issues and reducing surgery delays for burns. We have demonstrated a proof-of-concept prototype in our Capstone project, and it has been a valuable learning experience for engineering education. This is a major step in advancing wound care treatment, and you can find out more on our project website. We would like to thank the UCI Master of Engineering program and MEng-Matregenix for this opportunity.